Welcome to another session of water technology. Today we look into estimation of alkalinity in water. Before we move on, subscribe for more informative videos. Please drop in your comments after watching the video, and if you like the video, tap the like button. At the end of the session, you'll be able to explain the principle of estimation of alkalinity. You'll be able to describe the procedure and also perform this experiment. You'll be able to calculate the phenolphthalein and methyl orange alkalinity. You'll also be able to identify the alkalinity contributing ions and determine the amount of these ions present in the given water sample. We'll understand what is alkalinity of water. That is, it is a measure of the amount of hydroxide, carbonate, and bicarbonate ions present in it. Apart from this, silicates, phosphates, borates also include alkalinity, but which is not in major quantities. So we generally restrict ourselves to these three ions. This neutralizes the acidity in water. It is expressed as mg per liter or ppm in terms of calcium carbonate. And the significance of this experiment is mainly to determine the capacity of a stream or a river to neutralize acid pollution. That is, acidity present in the water. It can be due to acid rain or discharge of acidic impurities from industries, etc. This is the major significance. First, let us understand what is alkalinity. We say that it neutralizes the acidity in water. That means it is basic. So, I want to pose a question. What is the difference between an alkali and a base? Please press the pause button, think over the answer, then resume the video. Base neutralizes the acid, that is, we all know. One which has a pH greater than 7 up to 14, we call it as a base, and it neutralizes acid. But a base need not dissolve in water. If it dissolves in water, we call it as an alkali. So all alkalis are bases, but not all bases are alkalis. This is the difference. So we are discussing the basic material present in water, so we call it as alkalinity. So once I have said it is determination of alkalinity, that is base, we can easily determine it by acid base titration, a very simple titration. When you go for acid base titration, the two common indicators used are phenolphthalein and methyl orange, and this is the pH range. And phenolphthalein is pink in color in the basic condition and methyl orange is yellow in color. So if you take a certain amount of water, here I am telling YML, it can be 20 ml, 50 ml, 100 ml of your choice. If you take that water in a conical flask and add 2 drops of phenolphthalein, because alkalinity is present in the water, the color is going to be pink. And we titrate it against an acid, it can be sulfuric acid, nitric acid, anything. When we titrate it against an acid, the pink color becomes colorless at the end point, and we note down that as PML, that is the volume of sulfuric acid. So pink to colorless, it is becoming acidic. So this happens only up to the pH level of 8.3 when it's dropping down. But beyond that, if you have any alkaline substance, this phenolphthalein is not going to show us the endpoint. So we need methyl orange. So we add 2 drops of methyl orange to the same solution, and it's going to be yellow if basic substances are present, that is alkalinity is still present, and we titrate it further with the acid till it becomes reddish orange, or if you go beyond it goes to pink. It is better to stop at reddish orange, and this we note down as mml of sulfuric acid. This is phenolphthalein alkalinity. When you determine the burette is filled with sulfuric acid, conical flask, you take water and 2 drops of phenolphthalein. It can be hard water, because anyway if alkalinity is present also, it's going to contribute for hardness. And when you add 2 drops of phenolphthalein, it's going to be pink in color, and when you titrate with the acid at the end point, it becomes colorless. This is the indication, pink to colorless. And at the end point, we did note down the volume of sulfuric acid consumed as PML. And similarly for methyl orange, in the beginning itself we can add methyl orange, or after determining the phenolphthalein endpoint, we can add methyl orange to the same solution and continue the titration. And here the endpoint is yellow to reddish orange. That is, if alkalinity is present, it's going to be yellow, and at the end point it changes to reddish orange. This is the color change, and we note down the volume of sulfuric acid consumed at this endpoint as mml. And we have already said ions contributing for alkalinity, that the major ions are hydroxide, carbonate and bicarbonate. When we titrate it against an acid, we are indicating acid as H plus ions. Hydroxide reacts with acid to form water. Carbonate reacts with one mole of carbonate reacts with 1 mole of acid to form bicarbonate. This is important here. These two are indicated with phenolphthalein endpoint, but we are getting bicarbonate, so again it can react with acid to form carbon dioxide and water. So only half of this carbonate, only one part of the carbonate is indicated with phenolphthalein indicator, but the bicarbonate further reacts with acid to form this, which is not indicated with phenolphthalein. So the carbonate which is turned to bicarbonate, and as well as the bicarbonate present in your water, both together will react with acid to form this with methyl orange indicator. But in case you don't add phenolphthalein, if you add only methyl orange, all the three will get neutralized, because methyl orange can go up to 4.3. You can see with the pH, hydroxide when it's present is highly alkaline, so its pH will be about 12. And when the pH drops down, that is when you titrate against acid, and when the pH drops down to 8.3, that is your phenolphthalein endpoint, hydroxide and carbonate present is going to be neutralized, but not the whole of the carbonate, but the carbonate getting converted to bicarbonate, only that part. So we say that hydroxide and half of carbonate. Why half of carbonate? Because 1 mole of carbonate consumes 2 moles of acid, because one to convert to bicarbonate, another one to get converted to carbon dioxide and water. So it is 2 moles of bicarbonate. So phenolphthalein endpoint indicates the complete hydroxide neutralization and half of carbonate neutralization. Now if we further titrate it against an acid, when it drops down to 4.3 pH, that is your methyl orange, all your hydroxide and carbonate and also bicarbonate neutralizes, and below that pH we'll have free mineral acids and some dissolved carbon dioxide present in the water, which is not taken into consideration. At the endpoint of methyl orange, we see that all the three get neutralized. So what is M minus P? That is the volume of sulfuric acid beyond phenolphthalein endpoint, that is M minus P, indicates remaining half of carbonate and the bicarbonate neutralization. This is very important for you to understand. You need to remember this to understand the remaining portion of this presentation. Now, as we have seen, these are the three ions contributing for alkalinity. We see that all the three ions will not be present together in the water, and hydroxide and bicarbonate cannot be present together, because the hydroxide and bicarbonate combines to form carbonate again. So if these two are present, we'll have carbonate instead of these two. Okay, so for this reason we'll not have all the three present together, or will not have actually hydroxide and bicarbonate present together in the water. So what are the conditions present in the water? That once you have determined the alkalinity, the calculation is very simple. That is this is the general formula for determining alkalinity, which is expressed as calcium carbonate. That is the volume of sulfuric acid consumed for neutralization into strength of sulfuric acid, whatever is the concentration, 0.1 molar, zero point 0.1 normality, zero point 0.2 normality, etc. If you take it in normality, this is 50, which is nothing but the equivalent or weight of calcium carbonate. Because you are expressing the strength in normality, we are using equivalent weight. If you express the strength in molarity, you should take it in terms of molecular weight, which generally people don't do. Strength of sulfuric acid and 50 into 1000, because we want to determine the mg of alkalinity present in 1 liter of water. So 1 liter is 1000 ml. So this 1000 comes, and volume of water sample, whatever you take, 20 ml, 50 ml, 100 ml, etc. So if we are going to determine phenolphthalein alkalinity, so if water sample is yml, volume of xn sulfuric acid, that is the molarity of normality of sulfuric acid, if it is pml, Then phenolphthalein alkalinity is P, that is volume of sulfuric acid is P, strength of sulfuric acid is N, 50 into 1000 divided by Y, that is the volume of water sample. Similarly, methyl orange alkalinity, this volume of sulfuric acid is going to be substituted with M, that is the volume of sulfuric acid consumed at methyl orange endpoint. This is how you determine the alkalinity. Now we are going to determine, this is phenolphthalein and methyl orange alkalinity we have determined. But if you want to determine, identify the ions present in the water and how much of volume of sulfuric acid is consumed to neutralize that particular ion, then we have 5 different cases. That is depending on the P and M value. The first case is P is equal to 0. That is when I add phenolphthalein, it's not going to be pink in color, it's going to be colorless. So what does that mean? But I still say alkalinity is present in the water. It says that at phenolphthalein endpoint, hydroxide and carbonate, half of carbonate gets neutralized. If P is equal to 0, hydroxide and carbonate are not present. So what is the only possibility? That is only bicarbonate is present. So whatever is the volume of sulfuric acid consumed after adding methyl orange indicator, that is for the neutralization of only bicarbonate, because both hydroxide and carbonate are absent, only bicarbonate is present. So the volume of sulfuric acid is mml, that is the sulfuric acid at methyl orange endpoint. We'll go to case 2. P is equal to M. We are adding phenolphthalein. It is pink in color. We are titrating. It becomes colorless. Then we are adding methyl orange. And here, instead of turning yellow, it is directly reddish orange. That is, we don't have alkalinity further. That is, at phenolphthalein endpoint itself, it has completely neutralized. Then P is equal to M. Then we'll look into what are the conditions. When P is equal to M, P indicates hydroxide and carbonate, but M minus P, that is after phenolphthalein endpoint, if it consumes sulfuric acid, I'll have M minus P. But here it is not consuming any sulfuric acid beyond phenolphthalein endpoint. This tells that carbonate and bicarbonates are absent. So what is the only possibility? Only hydroxide is present. So this is how we determine, and all the sulfuric acid consumed is only to neutralize the hydroxide ion. So it is P and M, because both P and M are same. P is equal to mml. We'll go to case 3. P is equal to half of M. This is slightly tricky. Is equal to half of M. We'll take a value and understand. That is, in case P is 10 and M is 20, based on this equation. P is equal to half of M. P is 10 ml and M is 20 ml. So if you assume that only carbonate is present, for half of carbonate it consumes 10 ml. For remaining half, definitely it should consume another 10 ml. We see that M is 20. That means only if carbonate is present, 10 ml is consumed at phenolphthalein endpoint, that is carbonate getting converted to bicarbonate, and that bicarbonate further neutralizing. Okay, so M minus P is 10. P is 10 and M minus P is 10. So definitely bicarbonate and hydroxide cannot be present. So the only ion present will be carbonate, because half is consumed at phenolphthalein endpoint and remaining half is after phenolphthalein endpoint, that is M minus P. So the volume of sulfuric acid is only due to carbonate. To neutralize the carbonate ion, it is M or 2P. That is, it is M. M is nothing but 2P. 2 goes there, 2P. So it is M or 2P ml of sulfuric acid. Now case 4. Here you should be careful. P is greater than half of M. Already we have said if it is equal to half of M, only carbonate is present. If P is greater than half of M, already for half of M carbonate is present. If P is greater, definitely hydroxide is also present along with carbonate. And we have already said all the three cannot be present together, so only hydroxide and carbonates are present. And we should determine how much sulfuric acid is required to determine neutralize carbonate, and how much to neutralize hydroxide. How we'll do this? Here you should look at this equation and you should see which is the lower value, because this indicates as M minus P is beyond phenolphthalein endpoint. Okay, P is greater than half of M means this is greater than the sulfuric acid consumed after phenolphthalein endpoint. Okay, so the minimum sulfuric acid, that is when I compare these two, the sulfuric acid which is consumed after phenolphthalein endpoint is less. So we'll allot that for carbonate, that is half of carbonate. So if it is half of carbonate, M minus P is going to neutralize half of carbonate. I want how much it neutralizes for full carbonate. So for full carbonate, it is 2M minus P. Are you able to understand? We have already eliminated bicarbonate. So M minus P is nothing but neutralization of half of carbonate. But I want the volume of sulfuric acid for neutralization of full carbonate. Then for full carbonate, it is 2M minus P. 2M minus P. Once I understand 2M minus P, I know that methyl orange endpoint neutralizes all the three. So I can easily determine how much is the volume of sulfuric acid required to neutralize OH, that is M, minus the carbonate, that is sulfuric acid required for neutralization of carbonate, that is 2M minus P. M minus 2M, I remove the brackets, plus 2P, so I get 2P minus M. This is how I determine the volume of sulfuric acid required to neutralize hydroxide ion. So I know carbonate and hydroxide. The final case is P is less than half of M. Now this is less than half of M. That is half of M, we have already said it's only half of carbonate. So when this is less, it indicates this is more. When this is more, it tells apart from carbonate, bicarbonate is also present, because all the three cannot be present. The choice is carbonate and bicarbonate. Now we should determine how much for carbonate and how much for bicarbonate, that is sulfuric acid. Now again we'll go here. Which is the lower value, P or half of M? The lower value is P. So here P, hydroxide, is ruled out. At phenolphthalein endpoint, only half of carbonate is getting neutralized. So what is full carbonate? 2P. Are you able to understand? No hydroxide, only half of carbonate is getting neutralized. So for full carbonate, it is 2P. So this volume of sulfuric acid to neutralize carbonate is 2P, or 2P is nothing but M. Okay, sorry, it's wrong. It's only 2P. Don't take it as M. It's wrong. Avoid this M. It is 2P ml. Now we'll go to amount of sulfuric acid required to neutralize bicarbonate ion. So M is the overall neutralization of all the ions. So M minus 2P gives me the volume of sulfuric acid required to neutralize bicarbonate. Okay, these are the 5 cases and we are summarizing. That is ions present, volume of sulfuric acid required to neutralize a particular thing, and conditions, all the 5 conditions what we have seen, P is equal to 0, M is equal to M, and all these 5 conditions. And in this chart you can very easily determine the volume of sulfuric acid required for neutralizing a particular ion present in the water. So for one small example we'll take, this is the alkalinity formula, and we'll take an example. That is, if they give a problem and you have identified what is P and what is M. First you should identify how much is phenolphthalein endpoint and how much is methyl orange endpoint. Then you calculate half of M. This is 26, so half of M is 13 ml. Have these 3 values in mind. P is 15, M is 26, half of M is 13. We'll go back to the chart. That is, P is 15, so it is not 0. This condition is ruled out. P is equal to M. P was 15 and M was 26. These two are not equal, so this condition is ruled out. Half of M was 13, P is 15. P 15 is not equal to 13, so this condition is also ruled out. P is 15 and half of M is 13. So 15 is greater than 13, so our water sample is this condition. So we need not go to this condition. Already we have decided this condition. So we have hydroxide and carbonate, bicarbonate completely absent. So how much sulfuric acid is required to neutralize hydroxide? 2p minus m. And the volume of sulfuric acid required to determine carbonate is 2m minus p. Now we'll go back. So the hydroxide alkalinity we are going to calculate 2p minus m. This is volume of sulfuric acid. Are you able to see volume of sulfuric acid? Now we'll put it as 2p minus m, and all the other things remain same. Here I am taking the volume of water sample as 20, so I substituted 20. If it is 50, it will be 50. If it's 100, it will be 100. Similarly, for carbonate alkalinity, we'll see that is 2m minus p. Carbonate is 2m minus p. So I'll substitute volume of sulfuric acid as 2 of m minus p, and I'll calculate the carbonate alkalinity, and you should put the units as ppm or mg per liter. This is how any problem given to you, look at the p value, m value, calculate half of m, and go to your chart and see which condition satisfied, and accordingly substitute that formula, that is volume of sulfuric acid alone has to be substituted. All the other things will be the same, and you can identify the ions present in the water sample which contributes for alkalinity, and you can also individually calculate how much of sulfuric acid is required to neutralize a particular ion. This is all for this session. Thank you for listening. If you like the video, please tap the like button. Please do drop your comments. And don't forget to subscribe for more informative videos. Thank you. Let us meet again in another session. Until then, bye bye.